Ladies and gentlemen, my name is Eric Blanc. I'm an independent consultant based in Montreal, Canada. I am also the current chairman of the Technical Committee on Hydraulics of the IGS, and I will be the session co-chair for the session today. This session is titled Geosynthetic Testing and Properties.
Ladies and gentlemen, my name is Pietro Rimoldi. I'm a consultant working in Milano, Italy, and I will be the co-chair of this session together with Eric. I'm actually the chair of the Technical Committee on Reinforcement of IGS, but I have been the previous chair of the Technical Committee on Hydraulics. So together with Eric, we share a long experience in hydraulic application of geosynthetics.
So a couple of things before we start the presentations. You will have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able.
We also remind you that to claim PDH credit for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any session that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you received the proper credits.
Please enjoy the presentations.
Hello, this presentation being provided is on interface shear testing, specifying, review, and available ASTM references. There are 3 ASTM standards concerning interface shear testing of geosynthetic materials. The first, D5321, standard test method for determining the shear strength of soil geosynthetic interfaces by direct shear. The second, D6243, standard test method for determining the internal and interface shear strength of geosynthetic clay liner by direct shear method. These standards basically mirror each other in content except for considerations specific to GCLs in the D6243 standard. They are performance-based tests intended to model field conditions as closely as possible to provide project-relevant shear data. The third standard, the 7702 Standard Guide for Considerations when Evaluating Direct Shear Results Involving Geosynthetics, was developed to aid the reviewer of geosynthetic and GCL shear results. Being performance-based tests, ASTM D5321 and D6243 test standards are not prescriptive as to allow the test requester the freedom to specify the test conditions most appropriate to the project. Although both test standards do provide a checklist in its appendix to aid the test requester in specifying the shear test, it is worthwhile to note that some of the test labs performing these tests have their own test request forms similar to these checklists that can be used to specify the shear test. Information needed from the test requester to set up the interface shear test include information about the materials to be sheared, and instruction of possible conditioning of the shear materials, as well as the test parameters for the shear test. For interface shear testing, the actual products or materials to be installed or representative samples of the same material should be used. It is important to note that many products differ from one side to the other, and thus the appropriate side at the interface should be identified, such as texturing for geomembrane, the cap and carrier textile or membrane for GCL, the geonet structure or geotextile type or weight of a geocomposite, and whether a geotextile is heat treated. For product orientation, most products are installed in the slope direction, and thus the products are usually placed in the shear box in the machine direction. If orientation is different, this should be clearly noted. How product shear specimens are conditioned prior to placement into the shear box can be specified. This may simply be as received or wet it by pouring water over or spray wetting the specimen. For GCLs, the specimens can be partially hydrated to a specified water content or hydrated in water for a specified duration at a specified normal stress. If there is a soil layer as part of the interface test, how the soil is to be placed or compacted in the shear box must be specified to replicate how it would be in the field. This could be a specified field target density and moisture content, or the soil can be lightly compacted or tamped into the shear box, typically at the as-received moisture content, if the soil is simply being placed in the field by tracking it in without any specified compaction, or many times the soil compaction density and moisture content is based on soil proctor test results. If the shear test soil placement is based on soil proctor test results, the test requester must communicate the percent of maximum dry density and the percent relative to optimum moisture content the soil is to be placed. It is important to note that rock-corrected proctor values are not applicable, as the maximum soil particle size used for shear test is similar to that of the proctor test. For applied normal loads in which shear tests are performed, a minimum of 3 normal loads is required to determine the Mohr Coulomb shear strength envelope. These normal loads should bracket the range of project normal loads of interest for slope stability. Shear strength envelope plots provided in the shear stress versus normal load graphs are curvilinear. Thus, extrapolation of shear data beyond the range of normal loads tested would be unconservative. After the applied normal loads, there are 3 other shear test parameters that need to be specified. First, the interface saturation condition, which is the wetting condition within the shear box during seat time under test load and shearing. The interface saturation condition can be inundated with water where the interface is submerged in water, or the interface surfaces can be spray wetted during placement into the shear box, or just dry. Most often, shear tests are requested to be inundated with water, as this is the worst case, most conservative scenario. The second parameter is the seating, or also referred to as consolidation time, for shear tests with soil or hydrated GCLs. This is the duration of time that the test normal load is applied to the interface prior to shearing. The last parameter is the shear displacement rate. The rate of applied shear force should be slow enough to dissipate any excess pore pressures during shearing that may decrease the measured shear resistance. For interfaces where excess pore pressures are not expected, the test standards offer default maximum shear displacement rates of 5 millimeters per minute for geosynthetic interfaces and 1 millimeter per minute for interfaces with GCLs or soils. For interfaces in which excess pore pressures may be expected, such as with higher plasticity clay soils, the shear displacement rate may need to be slowed down considerably. Although not required by either shear test standard, certain properties for each interface material can be measured to provide better insight into the shear characteristics of that material. Shear results with textured geomembranes are directly influenced by the texturing of that geomembrane. Thus, asperity height measurements per ASTM D7466 of each shear specimen prior to placement into the shear box are typically included with the interface shear results. Below is an example of where 5 asperity measurements may be taken on a geomembrane shear specimen, with the average of these measurements being reported. Although usually not directly influencing the measured interface shear results, a shear test requester may want a peel test per ASTM D6496 for GCLs or a ply adhesion test per ASTM D7005 for geocomposites performed on the same sample the shear test is being performed. These index tests can offer an understanding of the product's bond strength needed to prevent the shear failure plane happening in the internal reinforcement of the GCL or the bond between the geocomposites GeoNet and geotextile instead of at the antenna interface. For GCL peel strength and geocomposite ply adhesion, it is recommended that the test specimens be taken adjacent and in line in the machine direction to the shear specimen. After the shear test has been completed per the test standards, the test lab is to report the peak and post-peak shear values at each applied normal load, plot of the shear force versus the shear displacement, plot of the shear stress versus normal stress with the adhesion intercept, the coefficient of friction and/or friction angle identified, test parameters for which the shear test was performed, and observations if necessary. The peak and post-peak shear values can be viewed for each normal load tested on the shear force versus shear displacement graphs. The post-peak shear values are taken at the end of the shear displacement distance. This displacement distance is typically 75 millimeters, as that is the limit of most commercially available large-scale shear machines. The identified peak and post-peak shear values for each normal load from the shear displacement curves are then plotted on the shear stress versus normal stress graph, and the best fit lines are drawn to provide the Mohr Coulomb shear strength envelopes. From the linear regression on the data points in the shear versus normal stress plots, the Mohr Coulomb friction angle can be calculated from the test results using the following equation. The shear strength equals the adhesion intercept plus the product of the normal stress times the tangent of the friction angle. From the example result provided, the peak friction angle is calculated taking the inverse tangent of the coefficient of friction in the first term of the peak shear equation, 0.5196, which equals 27.5 degrees. The second term provided in the peak shear equation, 397, is the adhesion intercept. Caution should be given to simply evaluating shear data based on calculated Mohr Coulomb friction angle without consideration of the adhesion value. Doing so may greatly underestimate the actual shear strength of the tested interface. Another value that may be included in the reported shear test results is the secant friction angle, which is the friction angle specific to the normal load tested. It is the angle of a line drawn from a data point on the shear stress versus normal stress graph to the origin and can be calculated with the equation secant friction angle is equal to the inverse tangent of the shear stress divided by normal stress. When evaluating test shear data with respect to a specified required Mohr Coulomb friction angle, the secant friction angles at each tested normal load can be an indication of whether the Mohr Coulomb shear strength envelope of the tested interface may meet the intent of the specified Mohr Coulomb friction angle. If the secant friction angles for all the normal loads tested exceed the specified Mohr Coulomb friction angle, then the shear failure envelope of the tested interface exceeds the shear strength envelope defined by the specified Mohr Coulomb friction angle. For an in-depth discussion of shear strength fundamentals, interpretation of adhesion, evaluation of shear displacement curves, comparison of shear results to historical data, and post-test sample inspection, see Standard Guide ASTM D7702. In summary, interface shear testing with geosynthetics and GCLs are performed using ASTM D5321 and D6243 test standards. These standards provide instruction of the equipment requirements, instruction on how to perform tests, and guidance of the information needed from the test requester to achieve project-relevant test results. When reviewing test results, Standard Guide ASTM D7702 is a helpful tool in understanding the test results provided by the Geosynthetic and GCL shear tests. Thank you for taking the time to view this presentation. If there are any questions, I can be contacted at the email address and phone number provided.
Thank you for participating to this presentation, which is going to summarize the work which was done in ISO 18283 based on the survey conducted with the IGS Technical Committee on Filtration to develop guidance for filtration with geotextiles. So first thing first, why do we need a design standard? Geotextiles have been used for filtration since the late 60s, early 70s in their modern format with polypropylene, polyester, polyethylene fibers. So, and there's been some design guidance developed since then. This guidance, the first guidance we could track were from the early 70s. So that's almost 50 years ago from now. So when we write an ISO or ASTM standard, we want to make sure that we're selecting the information which represents a consensus. There has been a lot of learning made in the last 50 years, so the ISO, the latest ISO or ASTM documents will reflect a consensus between the different users. They will also be there to educate, to help users who are not familiar with the product to identify the relevant concerns. However, it should be understood that because of this consensual approach, they may sometimes have to remain superficial, not to promote one particular position or view on a phenomenon. So they have to remain superficial somehow. ISO TC221 Committee on Geosynthetics did host the development of the standard I'm going to introduce today. It was done within WG6, Work Group 6, which is dedicated on development of design document for geosynthetics. This group includes 10 subcommittee or project group, to give the proper name. And the group on filtration is number 3, but as you see here, there are many other project groups. So this work on the design of geotextile for filtration was initiated in 2014, and Canada acted as a coordinator for this project. The meat we've used, the information we have used to develop this standard was based on existing guidance from different countries, from all the countries involved. So we had guidance from Asia, from Europe, from North America. We discussed which one should be the best. We've consulted different experts, and we have also performed a survey of the industry on the membership of the IGS Technical Committee on Filtration and of ISO TC221 to identify the most important aspects of filtration with geotextiles. So key findings of this survey. So first thing first, where is the survey coming from? Overall, we had over 200 surveys that were returned. The survey itself was coordinated by IGS. Eventually what we had was 200 returns. Most of these people, because of who we sent the survey to, most people were experienced with geosynthetics. And what we were happy with was a geographical representation. As you can see, we had a very broad distribution of representatives around the world, with people from Africa, Asia, Europe, North America, Oceania, South America. Most people, the vast majority, had several years of experience with geosynthetics, sometimes much more than 10 years. And also most respondents were highly educated with a university degree or more. We were also very happy with the balance between the different expertise with geosynthetics. So we had coastal protection, road drainage, foundation drainage, slope drainage, mine waste application, municipal solid waste, and others. So overall, as you can see, there is no particular group which is standing or which is underrepresented. First question was about the existence of a national guideline for the design of geotextile filters. What we found was that even if there are national guidelines in some countries, the majority of the respondents were not aware of their existence. And this, again, is despite they are educated and experienced in the particular field of geotextiles. We also found that there is no one group of standard, whether it is ISO or ASTM, which is standing against the others in terms of use. More or less, there is no unanimity on which group of standard is the most used around the world. We asked a question about failures. How many failures were witnessed in the last 3 years? And it was interesting to see that less than 30% of the respondents had a first-hand experience with a failure. Some people would have a second-hand experience that they've been involved in a failure, but they did not witness it directly. But only 30% had a first-hand experience with the situation. Of course, a little bit more with manufacturers because they are more prone to be called to resolve a problem, to find a solution. But still, it's not 100% of the users who found failures in the field. We also asked, we had a question about the confidence people have with the geotextiles. And overall, people are confident with the product, but we still found 20% of the respondents who were actually not confident with the solution, who would require more information, so who did not have a blank trust of the technology. From there, we asked what are the most important issues restraining the use of geotextile filters in your country. Overall, the analysis of the response led to the need to provide more education, more design guidance, which is exactly what we were wanting to do. So, as a conclusion, out of 200 responses to the survey, we observed the key facts that we took out from it was that there is a limited number of failures that were related to filtration performance of the geotextiles. Regulatory issues are typically not the biggest concerns. It may sometimes slow down the adoption of geotextiles, but it's usually not what is the most problematic situation. There is a lack of confidence. So it's not the regulation. It is actually the owner who are sometimes lacking confidence. They prefer a good, old, solid, thick layer of soil instead of a thin geotextile. It's a matter of confidence, not a matter of regulation. And finally, the last point was that there are some regional guidance available in more or less every country, but they are not always known. So education is really the key tool that should be considered to develop the appropriate use of geotextile. So the next question was, how can we better value the survey for the development of ISO 18283? Overall, the direction that were taken were to make sure the document is simple, prepared for beginners, and it gives confidence and adequately defines boundary where further testing should be conducted because we are in a special situation. So the ISO technical report 18283, which is on the design of geotextile for filtration, includes, based on all this analysis and meetings conducted within the technical committee, includes several chapters which are going to present now. Chapter 4 introduces concepts and fundamental principles. So we define what is filtration performance, ability to retain the soil skeleton and to let the water pass perpendicular to its plane, which is what has been always developed in every filtration criteria around the world. We want to understand the application. What are the type of soil, type of liquids used? The performance may vary with the type of soil and liquid. We have a survivability discussion. The product must remain intact after installation. It must resist mechanical stresses when applicable during service. And of course, it must offer a sufficient durability in the environment where it is used. We have defined essentially two key types of application. One is soil filtration, where there is an intimate contact with the soil, between the soil and the geotextile. And the second one is slurry filtration, when the particles reaching the soil are in suspension, in water or another liquid, and the filter has to retain some or all of these suspended particles to perform adequately. And this leads to very different design criteria. We have a chapter describing the materials, the key structures, so woven, non-woven, knitted, and we also provide a range of key properties, opening size, velocity index, which is a permittivity in the ISO world, percent open area, POA. We also discuss the number of constriction and so on. So we discuss the different material properties. In chapter 7, we identify the functional properties which are relevant to design. So these can be ISO, ASTM, or any other standard. So these are the properties related to the opening size, the velocity index, permittivity, permeability of the fabric, resistance to water penetration, number of constriction, for understanding that there is no full consensus on the relevance of these criteria. And finally, the percent open area for woven products. We then enter the principles of design. So we have general consideration. We are using the structure which was proposed by the Canadian Geotechnical Manual for geotextile filtration, and eventually modified by Michael Heibaum back in the early 2010, which made consensus within the group in the ISO committee that this was the structure best reflecting the mechanism involved for geotextile filtration. For slurry filtration, we found that there was no precise and reliable guidance available around the world. So basically, the way these products are designed are mostly based on tests and a combination of good practice in the field, good operational practice, and adequate design. For the design itself of the product, we have then in this chapter several steps which are reflecting the different actions to be taken to reach a proper design. First, define environmental conditions. We need to identify whether we have presence of iron, of organic matter, of suspended solids that may tremendously affect the performance of geotextiles. We have to confirm the installation condition. So having water runoff on top of a fabric before it's covered will affect its performance. So we identify those issues. Prevent abrasion, tear, cut of the geotextile before it's covered, etc. Of course, an important part of the environmental conditions is the soil properties. What kind of soil is going to be filtered. Once the environmental conditions are known, we can finally proceed with the design itself, which is to select an opening size or to verify the applicability of a given geotextile with a given opening size with a given soil, considering different equations. So the factors that you see on screen, the factors B, C, and E are defined in the standard depending on soil properties, depending on the application in some case. Like the permeability criteria, it depends on the type of application, on the expected hydraulic gradient. So the design guidance defines the retention criteria, the non-retention criteria of fines in suspension, and the permeability criteria. It also defines additional properties which are relevant for geotextile filtration, which are the resistance to water penetration and the POA, percent open area, for woven fabrics. As indicated, we also define situations where testing is recommended. And for that purpose, the chapter 9 indicates recommended tests to evaluate the performance of geotextile with given soil. So we have a short description for each of the tests you see listed on the screen, which may facilitate the work of users. In the last chapter, we identify material specification and design guidance which are used in different countries. So these are listed to facilitate interpretation and reading by potential users. To conclude my presentation, I strongly encourage users who are moderately familiar with geotextile for filtration to consult this document. It can be used with ASTM or ISO standard, or even with other material properties from other standards, if it's not ASTM or ISO. The content is at the same time comprehensive, but still simple to use. It will therefore help resolve non-challenging designs, and it will also define boundaries beyond which experts shall be consulted. So the publication of this guide, technical report I should say, is expected during the first quarter of 2021. So it's a matter of days before or after this conference. And so that would conclude my presentation. If there are any questions on this topic, feel free to send me an email. I was the person responsible for the coordination of the work which was presented here. So I'll be happy to answer any question.
Hello everyone, my name is Yue. Thank you so much for attending my presentation. The topic of this presentation is about laboratory mechanical property testing for turf reinforcement mats. Damage from mechanical impact on turf reinforcement mats occurs during the installation to the surface lifetime. During construction process, the turf reinforcement mats will be subjected to different kinds of damage mechanisms. Typical damage mechanisms include abrasion caused by repeated sliding action from an abrasive material, splitting caused when sharp-edged fill material fell directly on the turf reinforcement mats in combination with compaction with vibrating equipment. Puncturing occurred when sharp-edged material dumps directly on the turf reinforcement mats. Fiber cutting, tearing, and rupture exposed to large loads and deformations. One solution proposed to model the damage during the construction is to perform standard tests such as static puncture and dynamic perforation tests. This is the puncturing failure process of a woven fabric under a needle projectile. The damage of fabric includes the following steps. First, the initial steady increase in force with penetration of the tip due to contact pressure between the projectile and the fiber strand. Then there's a sudden drop of force due to slippage of the cylinder behind the tip into interfiber space. Next, another increase in force due to friction of the cylinder against the fabric. And finally, there's a steady decrease in force due to further penetration of the cylinder behind the tip. This is the 6 turf reinforcement mat specimen I tested in this study. Among them, only TRM-C is a general TRM, while other 5 are called high-performance TRM because of their higher tensile strength. HPTRM-F is the only multi-layered woven HPTRM with a unique corrugated structure. The basic index property obtained from manufacturer's brochures are listed in this table. In static puncture tests, TRM materials are prepared as 30 cm by 30 cm specimens. The test specimen was clamped without tension between the circular plates. The load was then applied on the center of the test specimen by a steel plunger attached to the load indicator. The specimens were then loaded at a speed of 50 mm per minute until failure occurred. Load displacement data are recorded every 2 seconds during the loading, and the puncture strengths are read directly from the load displacement curve. The figures on the right is the specimens after failure. The dynamic perforation test measures the resistance of geosynthetics to penetration by a steel cone of 45 tip angle dropped from a fixed height of 50 cm. The degree of penetration simulates the behavior of TRMs when penetrated by sharp stones. The diameter of the puncture hole in combination with drop height gives a measurement of impact resistance. That is, the smaller the diameter of the hole, the greater the impact resistance of the geosynthetic to damage during installation. The photo in the middle is the test locations for the TRMs that have similar weave structure. The pictures on the right is the specimens after dynamic perforation test. The load displacement curves of static puncture test results are presented in the figure on the left. The static puncture strength of each specimen is obtained from the maximum value of load in the load displacement curve. Among 6 specimens tested, HPTRM-A has the largest puncture strength to failure. HPTRM-F has the longest extension, while HPTRM-D has the shortest extension. Although these TRM specimens are made of polypropylene, they have different manufacturing methods and material density, which can also be represented by measured mass per unit area. TRM with greater fiber density have more fibers participating in load sharing and energy absorption during the static puncture test, thus leads to higher puncture resistance. The figure on the right illustrates the mass per unit area influence the static puncture strength in woven and non-woven geotextiles. This figure indicates that static puncture strength increase with the increased mass per unit area. This slide plots the correlation between basic index properties and puncture test results for the 6 TRMs tested. The results indicate that both static puncture resistance and displacement increased with higher mass per unit area and tensile strength. Woven TRMs with greater mass per unit area reflect more fibers within a specific area if it is assumed the material density is same for a single fiber. The static puncture damage will compress the fabric layer and then shear damage occurs the fibers on the top surface of fabric, while the fibers in the middle and bottom surface extended. TRMs with greater mass per unit area will have more yarns extending before shear damage happens, thus leading to greater puncture displacement values. The figure on the top left is test results of dynamic perforation test. HPTRM D and F have better impact resistance among 6 specimens. I also performed tests considering different locations, and the results are summarized in the figure on top right. The center is the weakest part for both HPTRM-B and TRM-C, while the edge of the lattice structure is the strongest part for them. This condition can be explained by the vaulted structure, which has a higher bearing capacity than the flat or concave structure. The maximum hole diameter decreases as the mass per unit area increases, but it appears to be largely independent of the tensile strength. This is the conclusion of this study. From this study, we can observe the measured puncture strength ranges from 3,400 to 6,800 newtons for the tested TRM specimens. We can also observe the higher mass per unit area shows greater static puncture strength and extension for woven turf reinforcement mass. Among 6 tested specimens, HPTRM D and F shows higher impact resistance to the dropped cone based on the smaller hole diameter. The measured maximum hole diameter values for the puncture TRMs range from 6.7 to 20.5 millimeters. While there is some relationship between the tensile strength and maximum hole diameter, the effects of weave structure and contact location affects it. It is suggested that the maximum hole diameter, puncture strength, and extension at failure should be tested and included in the TRM product reports, together with the basic index properties to help designers better select appropriate TRM products in practice. Thank you for listening to this presentation. Do you have any questions?
I am Thavachandran Shendan from Advanced Earth Sciences. I would like to thank my co-authors, Chris Kalnani from Advanced Earth Sciences and Professor Tim Stark from University of Illinois, Urbana-Champaign, for their valuable contributions for this paper. In my presentation, I will briefly talk about pros and cons of single versus multi-layer interface tests, typical composite liner configurations, the multi-layer interface test database developed, peak and large displacement strengths, comparison of single versus multi-layer interface test results for 4 sites, and summary and conclusions. What are the pros and cons of single versus multi-layer interface tests? Single interface tests provide a better understanding of each interface behavior. However, it requires multiple interface tests at each normal load. It could be as many as 5 or 6 tests depending on number of liner materials compared to one multi-layer test. Multi-layer tests directly measure the shear strength of the weakest interface, which can be readily be used for slope stability analysis. It saves time and cost, given that There are still some concerns among practitioners regarding multi-layer tests, such as shear strength parameters are only obtained for the failure surface. Some other interface may have moved or may have been close to failure. Critical failure surface may be different at different normal loads, and the discernment of this may be difficult to interpret from multi-layer interface tests. Shear displacement to reach peak strength in multi-layer tests could be much larger than in single interface tests, shortening the post-peak displacement and thereby possibly resulting in overestimation of large displacement shear strengths. I will mainly focus on addressing these concerns in this presentation. This slide shows typical composite liner configurations for bottom and side slope liners. Bottom liner typically consists of protective cover soil, a filter geotextile, a leachate collection and removal system layer with granular drainage media, a cushioned geotextile, a double-side textured HDPE geomembrane, a geosynthetic clay liner, an optional moisture barrier geomembrane, and compacted soil liner, which could be a low permeability clay liner or a foundation layer. The side slope liner typically consists of protective cover soil, a geotextile or geocomposite layer that acts as a cushion, as well as LCRS layer, a single side textured geomembrane with smooth side up, a GCL, and prepared subgrade. Sometimes double side textured geomembrane is used for side slopes for slope stability reasons. Multi-layer testing typically includes two soil layers with more compressible material placed in the upper half of the shear box. The geosynthetic materials will be floating between the two halves of the shear box with no clamping. For single interface tests, the substrate could be either a rigid block or a soil. Critical or the weakest interfaces we are interested in are soaked GCL versus textured geomembrane versus geotextile, textured geomembrane versus geocomposite, textured geomembrane versus compacted soil liner, smooth geomembrane versus geotextile. We have developed a database of 377 multi-layer interface test points from 18 projects. For the paper, we grouped the tests into 4 categories based on the liner system. GCL encapsulated between 2 textured geomembranes, unencapsulated GCL, subtitle D liner where no GCL is used, and smooth membrane overlain by geotextile or geocomposite. All the tests were performed at the same lab. The results, as presented in the paper, show multi-layer tests are consistent and repeatable. This extensive database can be used for initial slope stability analysis or design, but must be confirmed with site-specific testing. This slide shows shear strength versus shear displacement plots from single and multi-layer interface tests performed for one of the projects. The peak strengths and large displacement strengths are identified. The critical interface in this case would be geomembrane versus geocomposite, as it has the lowest peak strength. The foundation soil layer versus GCL interface has the lowest large displacement strength, but this interface would never fail. The peak and large displacement strengths from multi-layer interface match the single interface test results for the critical interface. The peak strength shouldn't be used for slope stability analysis where large interface displacements are expected, such as side slope or bottom liner under seismic conditions. Peak strength may be used for the bottom liner under static conditions. So what is the large displacement strength? It is the lowest post-peak strength at approximately 75 mm shear displacement. It should be noted that the large displacement strength is not the residual strength. This slide shows comparison of single versus multi-layer test results for a site with encapsulated GCL. Tests with GCL at as received moisture content shows excellent agreement between single and multi-layer tests, except under the highest normal load where partial internal failure of GCL was observed. The critical interface was GCL versus geomembrane at the highest normal load and geotextile versus geomembrane for all the lower normal loads. When hydrated GCL was used, the critical failure surface was GCL versus geomembrane for all the normal loads. The results from single interface were typically 10 to 15% lower than those from multilayer. For encapsulated GCL, average strengths from unhydrated and hydrated GCL tests need to be used for slope stability. The difference between the two methods were less than 10% for the averages. It should be noted that for this project, steel blocks were used as substrates for single interface tests. For all the other projects being compared, soil substrate was used. This slide shows the plots of peak to large displacement strength drop for the same site. With one exception, the results show excellent agreement between the two methods. This plot could be considered as a qualitative measure for adequacy of post-peak displacement. Shear strength versus shear displacement plots from the second site are shown in this slide. The bottom liner consisted of an unencapsulated GCL. There was no cushioned geotextile between geomembrane and LCRS gravel layer. Critical interface was hydrated GCL versus textured geomembrane. At the highest normal load, internal failure of GCL took place. The side slope liner consisted of a geocomposite layer on top of textured geomembrane. The critical interface was geomembrane versus geocomposite. Both sets of results show excellent agreement between single and multilayer tests, although displacement to reach peak strengths are slightly higher for multilayer tests. These plots show displacements at peak for site 2. The displacements are very consistent between the two methods, but the multi-layer tests tend to take slightly larger displacements to reach peak, as mentioned before. This slide compares peak and large displacement strength results from the two methods for site 2. Virtually no difference in the test results between the two methods, even with GCL internal failure at the highest normal load for the bottom liner. This slide shows results for another site with unencapsulated GCL. Critical interface was textured geomembrane versus geocomposite. Excellent agreement between the two methods in shear strength as well as shear displacement at peak. Site 4 consisted of a subtitle D liner with compacted clay liner underlying textured geomembrane. Critical interface was textured geomembrane versus geotextile. Results from both test methods show excellent agreement. Here, I show the comparisons from all four sites. The plot on the left side shows displacements at peak for multi-layer tests are typically 10 to 20 millimeters, which are most of the time slightly larger than those from the single interface test. However, both peak and large displacement strengths show excellent agreement between the two methods, as illustrated by the plot on the right. In summary, multi-layer interface tests provide reliable, consistent, and repeatable results for direct use of measured large displacement strengths for slope stability analysis. Multi-layer interface tests correctly identify the weakest interface as confirmed by single interface tests. Peak and large displacement strength envelopes compare extremely well between the two methods. Selection of substrate material appears to slightly affect the test results. For multi-layer tests, displacements at peak tend to be slightly higher. However, the large displacement strengths are nearly identical to single interface tests. The ratio of large displacement strengths to peak strengths is typically consistent for single and multi-layer tests. Displacements at peak may be affected by composition and type of GCL and bentonite type. More test data on different GCF products is needed to confirm this. ASTM standard has already incorporated multi-layer interface testing as an appendix to their latest update of test method D5321. Thank you.